So using collision theory, we will look at some of the factors that affect the speed of reaction. Okay, so we have these factors: concentration, size of the particles, pressure, temperature, and catalyst. Okay, so let's look at concentration first. Concentration, this one will apply to aqueous reactants, or your acid and alkali. Okay, increasing concentration of a substance in solution, there will be more particles per unit volume. So you can see this volume is fixed, right? This volume is fixed. And then this is less particle, less concentration. This is more particles, more concentration. So there are more concentration, more particles per unit volume. This will increase the frequency of collision. So if I have more particles, they can collide more readily. And this will also increase the frequency of effective collision per unit time. So when they collide, right, there will be more effective collisions also, and this one will increase the speed of reaction. This explanation over here, word for word, we have to write when we explain concentration using collision theory to explain the speed of reaction. Okay, over here I'm using particles. Okay, but if your question again is like HCl aqueous plus NaOH aqueous, your acid plus alkali, right? If I increase the concentration of the acid, there are more these particles. Please write it out. Okay, it's very general. We have to write it out. The particles in this example over here will be, there are more HCl molecules and NaOH molecules. Okay, we have to write it out. Please do not write particles. Be specific pertaining to the question. Okay, next factor that we are going to look at is the particle size. So how does size affect the speed of reaction? Okay, so this one will only apply to solid, because solid I can see the size increase or decrease. Okay, what happens when a solid decrease in size? When it becomes powdered, total surface area to volume ratio increases. So small size, large surface area to volume ratio. So there is more surface area to volume ratio for the reactants to knock against each other, right? Here I can knock over at the big sides, correct? But if I make it smaller, I can knock each of them, I can knock 6 sides, 6, 12, 18, 24. This one I can only knock 6 sides. Okay, so the explanation, right? Total surface area to volume ratio increases. So this one will increase the frequency of collision because there's more sides to knock on, thus increasing the frequency of effective collision per unit time, increasing the speed of reaction. Okay, decrease in size only affect the speed of reaction. It does not affect the amount of products formed. Okay, let's look at this checkpoint to illustrate why did I say that. Just now, that point is increase or decrease in size. Decrease in size do not affect amount of reactants or product form. Okay, so in a question over here, if I have 1000 cm cube of 1 mole per dm cube of acid, okay, and this one will react with 100 grams of marble. In flask 1, this one is using small marble chip. Small marble chip means decreased size. So flask 1 has decreased size. Okay, and in flask 2, I use a large marble chip. This one is increased size. So the speed of reaction, of course, this one is faster. Okay. Question asked me to sketch the graph of both reactions. So I'm using exactly the same concentration with the same mass, and I have to sketch the graph, right? So this graph, the red ones that we see is for flask 1. How do I know it's for flask 1? Look at the gradient. This is steeper than this, right? Gradient to the graph, the first red line that I draw is steeper than the second red line. So this is the faster rate of reaction. But the important thing is both reactions will end at the same point, right? The graph will not look like this. It will not double up. Okay? For these blue ones that I just draw, this is faster rate of reaction and concentration increases. Right? So if I have a higher concentration, when my concentration increase, the amount of products formed will increase. And that's why my graph, which is to measure the volume of gas, example, your carbon dioxide gas, should be higher.